All right, welcome to episode three, not two, of geometric or general relativity in geometric algebra. And this will be talking about connections. And if you recall from the covariant derivative, that this right here is the connection. And specifically, we will derive the expression for the connection bivector for the connection bivector. And that bivector is omega mu, and discuss the role of Christoffel syndrome, Christoffel syndrome. I can't say it. Christoffel symbols. Christoffel symbols. I can spell it right. I can't say it right or spell it right. Oh my gosh. Okay. So we are now going to just move to the next page. No, I don't want to waste that space. Anyway, recall that G mu equals partial mu x. So this is the coordinate basis vector, and it's just the derivative in the mu direction of the coordinate vector x. So recall this definition, and that the metric mu nu is just the inner product of the different uh, directions. So the metric, the coordinate metric, represents the mutual overlap, the mutual overlap of the coordinate basis. This is the coordinate metric, right? And so the coordinate metric can or represents the mutual overlap of the coordinate basis, which is seen in this equation right here. Then the Christoffel Christoffel symbols are defined as follows. You have gamma, beta, and then you have mu alpha, and this is defined as 1/2 superscript metric, beta lambda, and then you have partial mu, so the derivative in the mu direction, alpha lambda, plus derivative in the alpha direction, and then mu lambda, and then minus derivative in the lambda direction, g, and then alpha mu, like so. It would select. So these are the Christoffel syndrome symbols. I don't know why I can't say Christoffel symbols. I don't know why it's so difficult for me to say. It's really annoying. But let's talk or consider what this is. So this right here is the rate of change, which I'm just going to call the ROC now, in the G mu direction, or I'll say along of the G alpha and G lambda overlap. And then this right here is just going to be the rate of change along the alpha direction of G mu and G lambda overlap. And lastly, we're going to have exactly the same thing, that this is the rate of change along the gamma lambda direction, or an alpha mu overlap. So what the Christoffel symbols do is they take these rates of change, where you have the rate of change along the mu direction of alpha and lambda, and then alpha and then mu lambda. You have the different combinations. So you have these different rates of change added together, and then you have them up, you have them summed over the overlap with some vector that is different from all of these, and you see how the changes in overlap here affect this overlap. So that's what the Christoffel symbols are doing, is they're looking at how, when things change, the overlaps change, or how the overlaps are affected. So how the metric is affected by all this change in the metrics. All in the metrics. Yeah, it's metrics. It's the plural. So we will use these Christoffel symbols because they play an important role. We'll use the Christoffel symbols. Christoffel symbols, since they play a, a an important role in the following identity, which is important in general relativity. And I don't know if this has a name, but I'm going to call this the Christoffel identity. So yeah, this is what I will call the Christoffel identity. And this Christoffel identity is going to be incredibly important for our calculation of the connection bivector omega mu. All right, so to derive an expression for omega mu, or to derive an expression for omega mu, we must first take the covariant derivative. First, first, first. Okay, man, I'm not in spelling shape today. Take the covariant derivative of the tetrad basis. Of the tetrad basis gamma m. So there are two main results that we can get from this, or we have to take it two different ways, and we'll have two expressions that are equal to each other. Or there we go. That about in the middle, and about in the middle. So we're taking the derivative in the alpha direction of not gamma mu, sorry, gamma m. And this is just going to be the space-time derivative in the alpha direction of gamma m plus the connection omega alpha gamma m. Well, the cool thing about the tetrad basis is that this is a basis for the space-time algebra. So this is the basis for the space-time algebra. And the basis for the space-time algebra, its space-time gradient is always 0. It doesn't change. It's a constant basis. So we're going to get 0 for this first term. It's going to vanish, meaning that we're just left with the connection term. Now we're going to take this. We're going to take this. I don't know why I copied this part. I don't need it. Okay. And we are now going to expand the definition of gamma m. So recall that gamma m is defined as the verbane, which is going to be E mu E m, and then it's going to be G mu. And this is just going to be the covariant derivative of the verbane times Gm. So in this convention, it's only operating on exactly what it's to its right. And then plus the verbane. I think I'm pronouncing that wrong. And then times Gm. So we can already see that the Christoffel identity is going to be used here. But notice here that we have the covariant derivative of a scalar quantity. This right here is scalar. And so the derivative of a covariant scalar covariant derivative, well, you're going to have the derivative term, and then you're going to have the connection term. But the commutator of a scalar is 0. So we just are going to end up with this term. So we end up with partial alpha E mu m g mu plus, and then E mu m, and then Christoffel symbol mu alpha g beta. And so we have that these two quantities are equal. So therefore, this quantity is equal to this quantity. Now, we want to isolate omega alpha, which is the connection bivector. So to isolate that, we need to use two identities from geometric algebra. So the first is because omega alpha is a bivector and gamma m is a vector, it follows that the commutator omega alpha gamma m is actually their inner product. Because the commutator of any object returns an object of the same grade. And so this is grade 1, which means that this whole thing needs to be grade 1, and the product of something in grade 2 and grade 1 that returns something grade 1 is the inner product. So this is the inner product here. And it anti-commutes, so we have minus gamma m dotted with omega alpha. And then the next identity is if we have a vector in the space-time algebra. I can do a better element. There we go. And we have a k vector. So it's an element of the k graded space. Then the inverse of A times A dotted with this k vector is going to give you k times the k vector, where this k is just an integer. So we have two statements here, and we can then say, or I didn't put this in the center, we can say that because, therefore, by the fact that gamma, the inverse of gamma m, is by definition the reciprocal tetrad, it follows that if you multiply omega alpha gamma m, it's just gamma m, or minus gamma m dotted with omega alpha, which is going to be minus 2 omega alpha. And this is the identity that we need. And so we can just multiply by gamma m on both sides of this equation to isolate or omega alpha. So let's do that. Therefore, minus 2 omega alpha is equal to gamma m partial alpha e mu m g mu plus gamma m e mu m, and then the Christopherson symbol beta mu alpha g beta. And we can keep simplifying this. So I can pull in the vector here because the derivative of this vector is constant. Recall up here. So this is 0, or so we can pull it in to this, and we end up with g mu plus e mu m gamma m beta mu alpha g beta. Dang it. And then we can, this is the definition of g mu. So we get partial in the alpha direction of g mu, And recall that by convention, we have the parentheses there, plus G mu, mu alpha, G beta. And now we're going to plug in the Christoffel symbol. So I'm going to come up here. It's a little bit big. We're going to have partial alpha G mu plus. Then we're going to have this here, 1/2 out front. Then we have G mu, like so. Oh, and then G beta. Now we can actually sum over this beta index and remove it. So we end up with basically, I don't want to rewrite everything here, so I'm going to just copy and paste. So we have that sum to get rid of the G beta. And we can now do one more thing because we know that this is equal to a bivector. And right now, as this product stands, this will give you, in tensor notation, this gives you objects that are both scalar and vector. And so what we're going to do is make use of the fact that we're in geometric algebra, and we are now going to say that, well, we're selecting the grade 2 because we know we're in grade 2 already. So this is something that you can't usually do outside of geometric algebra, but now we can. So what we quite literally do is say that, okay, we're going to take this quantity, and we're now going to only consider things that are grade 2. So before here, these are technically geometric products. And the products between here and here are geometric products. Or actually, these are all scalar, so I don't know why I said that. But these are geometric products, and this is a geometric product between these two. So now we're going to just select the stuff that gives us grade 2. This is a vector, this is a vector, this is a vector, this is a vector. So we're just going to select objects. We're just going to select the outer product. So now we have partial alpha G mu wedge G mu plus 1/2 of G mu wedge G lambda. And then all of these fun guys right here. And that is that for selecting the grade 2. But now we need to prove another thing. First off, that this vanishes. So this will vanish. So how do we demonstrate that? Well, it's actually because of a little fact here. So if we have G mu wedge G lambda, so we're just going to apply this to this coefficient here, partial alpha G mu lambda. Well, then this is just going to be equal to 1/2 G mu G lambda minus G lambda G mu partial alpha G mu lambda. But we know that because this is just the metric here is just an inner product, so it's symmetric in swapping its indices, meaning that these are equal. And this means that G lambda G mu partial alpha G mu lambda, well, that we can actually just copy this, copy it, and then just swap its indices. But recall that indices are arbitrary. And so we can swap indices. So as long as they're different, so lambda and mu are different, lambda and mu, but we could just relabel this and say that it's G mu G lambda partial alpha G mu lambda. We can just say that we relabel it by swapping the index order because indices are arbitrary. So that means that this quantity here, or this quantity, I'll just copy this. Now, because of this property, this times this is actually equal to this times this. So this whole thing is equal to 0. So this is the little property that we needed to prove beforehand. And then let's put this in a box. So now we know that this is going to go to 0, so we can just remove it in our next line. So I'll just copy and move this stuff around like so. And now we have one last little bit of rearranging that we must do. Or we have two. The first is that we're now going to multiply by negative, or we're going to divide by -2 here, so that we end up with omega alpha and then all the stuff we need. So all the stuff that we've done thus far implies that omega alpha is equal to -1/2 of, what do you call it? -1/2 of, okay, partial alpha. I lost my track of where I was in my notes, so I had to go back for a second. Then -1/4 G mu wedge G lambda, and then this. Well, what we can do is absorb the negative sign into this outer product by just swapping the order of the products. So this is just going to be 1/2, and then we're going to have G mu wedge partial alpha G mu, where because this is scalar, it's known that the outer product here is of this whole thing, then plus G lambda wedge G mu, and then of partial mu G alpha lambda minus partial lambda G alpha mu. Actually, I forgot a factor of 1/2 here. So we have this. You'd think that we're done, but not quite. We have one more thing to do, and that is to simplify this expression right here. So we have 1/2 G lambda wedge G mu partial mu G alpha lambda minus 1/2 G lambda, wedge G mu, partial lambda, G alpha mu. This is equal to, actually, what I'm going to do here is change the color just so that it's more obvious. And we're going to make this positive. So we swap the indices here. But then notice this, we have same indices here, same indices here, same indices here, here, and here are the same. And so if we just relabel this right-hand side, then we end up with, oh, we end up with, end up with 1/2 this plus 1/2 this, which is just going to give us 1 times that quantity. And what does this quantity look like? Well, we can actually rearrange the parentheses, because recall this was scalar, so we can move it inside this parentheses, these parentheses, and this is the definition of the space-time gradient. So we get G lambda wedge the space-time gradient of alpha lambda, so the metric. So therefore, the final answer is this. So therefore, omega alpha, the connection bivector, is defined as 1/2 G mu wedge partial alpha G mu plus G lambda wedge partial G alpha lambda. And this is the result of the video. So this is the result. This is the simplest way I've ever seen to calculate this, which is saying something because it was not like it was a short calculation. It was pretty long, in fact. But it has a very clean geometric interpretation that is harder to get in a general relativity's traditional tensor formalism. In here, you have the coordinate basis and then wedged with the change of the coordinate basis in the alpha direction. So that's telling you that the generator of, or that one component of the generator of the curvature of the, so this generates the rotation, the Lorentz transformations for the connection, and that in turn is the result of the curvature. And so the curvature here is a result of the coordinate basis, it wedged with where it's changing. And this creates the plane of changing. So if you're thinking about this in a spear-based geometric view, then this would be the plane of rotation. And then if you're thinking about this in terms of hyperplane based or mirror based geometry, then this would be the axis. Um, this would be the hyperaxis of rotation. And if you're thinking about this right here, or this term, it's then looking at, okay, now you have another direction that's not the same direction as this. You have this direction, lambda, and you look at its overlap with the direction alpha. You look at the overlap and you look at how that overlap is changing in space. And then you look at that resulting vector, which encodes for the changing overlap, and then you create you wedge that with the coordinate. And so this conceptually is very similar to what this is doing conceptually, which is that the omega alpha, which is accounting for this curvature and the connection, it is taking the coordinate basis and then creating a plane of rotation with where the curvature is changing, where the coordinates are changing.